think this is what is our present challenge, and we have done some progress in this direction. Because if you perform polymerization generally in an ideal solution, generally you can get a binomial distribution, where the distribution of the peptides of the polymers will be like in a Pascal triangle, where the wings of the triangle, for the monomer, dimer, trimer, tetramer, pentamer, hexamer, are representing the homochiral peptides, homochiral polymers. If you take, let's say, racemate and you polymerize a racemate, if you look on the composition of the dimers, the trimers and tetramers, if this is done in an ideal solution, then you will see that you're going, for example, the primary, then take one which is homochiral, the one which is poly-S, and in the middle you have the heterochiral peptides. And if you go, let's say, to hexamer, almost you don't see, or you go to octamers, you don't see the homochiral peptides. Now, there may be some kind of departure from that, because as you start polymerizing the system, you might have some kind of what we call in asymmetric synthesis, you may have some kind of asymmetric induction. But mathematician will say, Jim is not here, I think build a very nice model where you can say a Markov mechanism. But maybe if you form RRR, R can really induce asymmetric induction, and then you continue, then you get some kind of departure of this binomial distribution, and you get a small excess of some of the R's, or poly-R's and poly-S. But generally, actually, in order to build up, and I think this question was raised before, in order to build up an alpha helix, you need at least 8 repeat units of the same elements to build up a stable alpha helix. To build a beta sheet also, I think this was Doty and Loud, they did a lot of studies in this direction. Then beta sheet also you need 8 repeat units. Murray Goodman and others, they've done this 8 repeat units in order to build up a beta sheet. And the question is if in such kind of a random polymerization of the system, whether you can build up 8 repeat units of the same randomness, because George Wald actually pointed out at the time that if you have, let's say, an helix of 8-10 units, you might have some kind of an asymmetric induction, and then once you have created such kind of an helix, you can have an asymmetric induction, and this asymmetric induction can result in the formation of a peptide of a single or polymer of a single randomness. And the question we ask ourselves, how to generate this, how to overcome these drawbacks in the early stages of the polymerization. And to say, since I came from the crystallization, from the crystal world, I used to say, well, if you form some kind of aggregate of some kind, and you form some kind of a cluster of some kind, then you may, by the formation of this cluster, you can overcome this problem. And this was my view until yesterday, because yesterday it changed my mind. Now I have to take into consideration maybe other kinetic mechanisms of the kind that you responded, but I still believe that the mechanism of the formation of self-assemblies of some kind, right, can generate, it can lead to some nonlinear kinetics, and these nonlinear kinetics can break.
You want to have an outside order,
yeah,
impose an inside order. Exactly.
You pass it very nicely. So we have done 2 parts of this, actually, and I say, in my previous lecture, I already pointed out that we're very much interested in the self-assembly of molecules at their water interface. When we started these studies, what we had in mind, our tool were actually surface tension measurements. The surface tension measurement gives you some information about how much of the molecules can accumulate in their water interface, but they don't give you some information about the structure of these clusters which are found in their water interface. And since we are also interested in what we call in crystal engineering, we don't like to do the experiments blindly. We say, if we know the structures of these clusters, can we design the clusters for a certain purpose that we are interested in? And one of the purposes here was how we can design experiments where at least in the first type to get poly-R and poly-S and excess, and then in the second point to try to break mirror symmetry to get just one out of the 2. So our idea was, let's say, to go to the air-water interface, and I think this could be some kind of relevant system because we do the experiments in water, and we want to do the experiments in water. And you say, well, take, let's say, a racemic mixture of some molecules which are amphiphilic. We know that this could happen also with amino acids themselves, but since the method of grading angle diffraction and the synchrotron, we need a sufficient number of electrons. We decided to go to longer chains, which we could analyze experimentally and then perform by analyze the product. Now, if you form some clusters, and these are not Langmuir films, because in Langmuir films, what you do, you compress the system. These are pure self-assembly. In all what we did during our 10 years, 15 years of interest in this, what we call crystallography in 2 dimensions of the robotic interface, we did it on self-assemblies. Because this is, pressure does not relate to that, but we wanted to understand the really self-assembly of the system. And then the first part was that if we could really select groups which can react in the water, if we just activate these particular groups in the water, you inject the catalyst in the water solution, you polymerize, and then you have to go in to analyze the product. But if you're dealing with DL, you would like to know how to analyze the product. And for that reason, this is why you have so insisting mark in your study, how many deuterium you want to have in order to be able to form. Now, it's not to have this particular separation between the two. We labeled one of the enantiomers with deuterium. If you do this, let's say, lysine with that stearic acid, you took fully deuterated stearic acid, which might have 36 deuterium atoms. And then, in this way, you go to the multi-top mass spectrometry, and you can analyze the entire distribution of the polymer that you're forming. And the first question was, because we knew about this work, we knew about the problem of polystyrene. My colleague Jacob Klein in the laboratory actually was assembling polydeuteurated polystyrene and polyhydrogenated, and he had fast separation between the two, using this what called helium. What that?
Didn't he go to Cambridge now?
No, he returned back to the Weizmann.
He came back?
He came back.
He left, but he went to Cambridge.
No, he is now my neighbor. We're sharing offices together.
One question concerning pressure. This is interesting. You said you don't want to have pressure.
No, I don't. I want to have a situation which is more realistic, if you like.
Yeah,
we have done this also on the pressure, but what we say that would take 50% coverage of the surface.
You're an expert on the question. I don't know what's the general case. Does the homochiral packing of molecules usually lead to lower specific surface?
I will come to that. I will try to answer this question. On the size of the cluster of the homochiral resolution, I will come to that point.
Okay.
Okay. So what we done at Pompey was we labeled one with deuterium, and one we left non-deuterated. We polymerized that, and if you go to the multi-top mass spectrometry, you can detect the homochiral one, which are fully deuterated with the highest mass, the undeuerated with the lower mass, and all the others in between. And what you could not, in these conditions, we could not differentiate between a heterochiral one of different sequence, but then we went to multi-top measurements with a colleague of mine in Paris, Gerard Bach, who did multi-top. Now, what he cleaves the chains, and from the various sect of this chains, he was able also to learn something more about the sequence of this. Interestingly enough, many of these systems form blocks of copolymers. They don't form completely random polymerization, but they form blocks of polymers, as come out from these multi-top experiments. So the compound that we use here were N-carboxyanhydride of, let's say, C18 glutamic acid to C18 lysine. And also we use the thioesters, because the DUE actually suggests, and people believe, and also I think Wachtenhauser now and others, I think also the Montpellier group, they also believe that N-carboxyanhydride and the thioesters and the thioacids themselves could be a very good ingredient to start with. So actually the first type we tried to go to build up on these particular molecules, okay? Where again labeling the side chain with deuterium and performing the experiments. Now the first example that we looked for was to find a system which undergoes spontaneous resolution. Now to try to build up a system where the L and D will undergo spontaneous resolution in 2 dimensions, like what you have in 3-dimensional crystals. Okay? And then we say if you form separation of territories in the beginning, Then if you found the separation of territories in the beginning, then you're going to get poly R and poly S. Okay? And then we went to this, to C18. We went to lysine. And the reason why lysine undergoes spontaneous resolution, because you have this amide bond, which forms an hydrogen bond, and the hydrogen bond defines a translation axis, which is axis of chirality, and then it forces the molecules actually to crystallize along one axis of chirality, and then the CONH defines another axis of chirality. So you have two hydrogen bonds, which one define two translation axes, and force this molecule to undergo spontaneous resolution. Because if add air water interface, yeah. And for this way, what you could engineer that. If you go to the ester, where you don't form that part, actually what happens is, because this chains, the hydrocarbon chains, has a very high tendency to form a herring bond. And the herring bond between these chains takes place along a glide plane. If it takes along a glide plane, you define a mirror, and therefore this glutamic acid and carboxyanidride, they crystallize in the centrosymmetric. Not a centrosymmetric, because you cannot have a center of symmetry, but along a glide, no achiral space group on the problem. So first of all, we had this idea. Let us try to generate the system, and we shall see the problem that Gunther just laid it out. We performed diffraction of this. These are X-ray grading angle X-ray diffraction measurements of steroid lysine, and as I pointed also in the other way, that you can see that the R and the RS have a very similar diffraction pattern. There is some difference here about the tilt angle of some of the chains in the pure L, on the pure L system, but it's clear that they are very, very similar to each other. So now the problem, then we perform the experiment, and if you go, for example, in the case of the steroid glutamate, you see a very big difference between the DL and the L. So this is a racemic compound, this is a spontaneous resolution in two dimensions, okay? So we try to polymerize the lysine, because if you have this kind of separation of this cell problem, and what we found that we could generate, in the case of the lysine, only about 6-8 units. 6 repeating units of the problem. And the results were not very good. Because if you do the histogram of that problem, this is what is expected from the binomial distribution. And what you see that in hexamer you found a little bit more. It depends on the temperature, but the results were not very good. We could not get more than 6 units. And then we tried to understand why is that. So we went to measure, we could measure one equivalent length of these clusters. And the equivalent length of this cluster was very small. This is what actually we pointed out. There are 18, this is only 15 to 30 nanometers when they undergo spontaneous resolution. This was 15 to 30 nanometers. And of course, on the periphery of these clusters, you might have molecules which will be a different organization, and maybe this was the reason why you were not able to get this larger number, higher, let's say, molecular weights, and better separation, better stereospecificity, right, and entropy. On the other hand, what we found, that if you go to the racemic compound, the clusters are much larger. They were 80 to 100 nanometers in diameter. They're much more robust in a way. And we asked the question whether we can use these racemic clusters, in order to obtain this particular poly R and poly S system. And in principle, this should be possible, because if you take a racemic crystallite, in this racemic crystallite, you have the poly R chains, and you have poly S chains. Poly R chains and poly S chains. Now, if it is a random distribution, of course, you have a mixture, and we can see that we found some system which give a mixed solid solution, which was a real disordered system. And then you find that you can have the syntactic polymerization, where R reacts with S, S reacts with R with S, R with S, and we getting a syntactic poly R, poly S, which for the sake of our interest is not the one that we are interested in. We are interested in this particular system. And in this we found one system, which was the thioester of lysine. And in thioester of lysine, we found that there was a difference between the DL, the spontaneous resolution, well, between the enantiomorphous phase and the racemic one. And we decided to take the racemic one and to see how this racemic one, whether we can get poly R or poly S. And this also could give us some information about what is happening, because, you know, for years, when we were investigating polymerization in solid phase, you mentioned a little bit more of it. I remember a long time ago when I was doing my PhD, he was one of the players in this problem. People at the time were expecting that if you perform polymerization in a crystal, only the dimers and trimers are actually controlled by the crystal. There were very few examples where you could get beyond the dimer and beyond the trimer to get something which is really controlled by the crystalline levels. Okay? And therefore, we wanted to see how much we can go with that. And this was the structure that we had, that we could solve from these particular clusters. And we found that the molecules are related in one way by translation, and which will give the poly L or poly R or poly S, and the one by glide, which will give you actually the syntactic one which we got. And what we observed actually was that this was a distribution. Again, we got no more than 6 repeat units, but again, we could see, let's say, from the trimer, instead of having 1 to 3 to 1, we got 1 to 1 to 1. It was a nice stereospecificity, and the tetramer, for example, we could see that really it was very, the homochirals were pumping out. They are the major components of the system. And then if you go to the pentamer, to the hexamer, still the homochirals were actually observed. If you take the glutamic acid, acid, it forms a mixed crystal, dissolved to the solid solution, and you see that you get something which is, you don't get the octamer and the system. Again, these are demonstrated that one can use racemic systems in order to be able to deal and cope with this particular problem. Something very recent, very similar to what I demonstrated before with crystals. That we could also use the centrosymmetrical crystals for Smirnov symmetry breaking, and we shall see that we can continue to use that factor also for the solving the problem as we want to solve it.
Yeah, I'm confused about something.
Okay.
Thing I can't. What are these red bars?
Okay, what is this one? This is the molecular dimer. And this is the relative intensity of the peaks that we get in the mass spectrum. So this is actually the protonated, fully protonated dimer. This is the fully deuterated dimer, and this is the mixed one.
So those are mixed.
Yeah, what you have in between, these are the mixed one.
So
what you have on the wings, these are the homochiral one.
Yeah, so you're not getting a very high.
No, in this case we didn't got very high system.
No, not all of them, but you're not getting a lot of homochiral.
Well, actually, if you compare this to the binomial system, if you go to the tetramer, you get 1 to 4 to 6 to 4 to 6. Here you get the homochiral one as the measure component.
So it's a tendency toward.
There is a tendency to this particular part.
Do you see that better with the thioester than you do with the regular ester? The amide, I mean, with the thioester?
No, with the problem.
Not the ester. You see it more with the thioamide than you do with the amide?
No. I think the problem is that in the previous case we had a spontaneous resolution, so the size of the clusters was very, very small,
so
and this was not good. Here is the ester, just the ester, which we feel is not as good as in the case of N-carboxyanide, as we shall see immediately. Okay. So now the next problem that we wanted to do is that, okay, we wanted to know what happens if I take a non-racemic mixture. If I take a non-racemic mixture, like what you show about this Pelican experiment and Cook's experiment that they did, they took non-racemic system and they sublimed it. Actually, we asked the question, what would happen if you take a non-racemic mixture and you deposit this on the air-water interface? Are you going to get a phase separation? Are you going to get, let's say, a racemic crystal, which one of the part of that will be a racemic crystal, and the excess will crystallize, will appear as a new phase, which is the enantiomorphic phase. And if this is the case, if in the racemic crystal we could design a system where the racemic system will give you a syntactic polymer, all the small excess that you're creating, what you have in this mixture, will give you a homochiral polymer. And this experiment was much more successful, because you see here, if you have, let's say, a structure where R will act with S, R with S, R with S, you're going to get a syntactic polymer, which is not interesting. Okay, syntactic polymers. Whereas the isotactic one will be actually polyar. I mean, all this excess that you have in solution of this non-racemic mixture, all the excess will result in the formation of polymers in a single element. Very similar to this experiment in 3D crystals that's been done about that you have phase separation in the system. And I say here...
What's the difference between the left and the right? I missed that one.
if you take R larger than S, R and S would have a tendency to form a racemic crystal, whereas all the excess of the R will give you a crystallite, which is poly-R.
In other places, you mean?
In other phase.
Yes.
And then what happens is then if you inject now the catalyst, and if this phase is arranged such that it can give you a syntactic polymer, this one will give a syntactic polymer which is not of interest, whereas all the excess that you have of this S, of this R, will give you the homochiral peptide.
Yes.
So this is a way that you can make an amplification, if you like. You can announcement of
and
the...
You want to get rid of the syntactic ones, yeah?
No, they don't. If they are formed, they are not interested.
So,
but what you want, want to generate this part. And then what we did here... Okay. Again, we saw the structure, we took the carboxyanides, steroid glutamate, which I told you, and we did a diffraction pattern of that powder. And we see the crystal structure of this cluster, and the crystal structure of this cluster. And in this cluster, what we found was that R and S along the glide can form a very nice syntactic polymer, because this can go along this pathway to give you the syntactic one. Whereas here, no matter what will be the mechanism within this particular cluster, it will give you the R. And then, here are the results. This was 1-to-1. And this is the pure racemic one. And you can see in the pure racemic one that the heterochiral, which is probably the syntactic, was formed in large excess. It was not 1 to 2 to 1, but was 0.1, 0.1 to 0.8. And when you come to the 12 repeat units, the wings were not formed whatsoever. But you see that very nice distribution for the formation of a syntactic polymer. Now what we did is we took 3 to 7, and what we see the distribution of the polymers which were formed, the short one were rich in the heterochiral one, but when you get to 10 units or to 9 units, you could find only 10 homochiral and 9-1, but all the others were missing. Okay? So in this case, it was a nice system. In other words, to take a non-racemic mixture, to obtain separation of phases, and then you polymerize the two systems. One gives you something which is syntactic, and the excess gives you something which was completely homotactic. Well, these were nice experiments. However, we were not... there was another experiment. We were able to do this phase separation into a phospholipid membrane. You just take the phospholipid membrane, and then you put the DL, the non-racemic one, and what you could find, a phase separation. You could see the phospholipid, you could see the DL, you could L. Now, very nice phase separation at the water interface, and when you do the polymerization reaction, we got results which were quite similar. Okay. Now, the point was that we were not happy. We were not happy because the molecular weight was not very high. We wanted to get very high molecular weights in this particular system. Then we decided to go to the crystal polymerization. Now, as I say before, polymerization in crystals are not very useful because they were quite disappointing, I think, in the 60s and the 70s, because these polymerization reactions are taking place, are controlled by the crystals only at the very early stage of their formation, the dimer, the trimer. But when you go to the longer one, they were not actually controlled by the crystal. But I look at the crystal of phenyl N-carboxyanide, which was published by Kanazawa in Japan. Oashi. And then when I look on the packing arrangement of this crystal, I know intuitively, I thought that might be a very useful method to get high polymer signal. When you look on the crystal structure of this anchor boxionide of phenylalanine, what you can see, they are forming actually rows of S molecules, where the H is pointing in one direction. Now this row is polar in one direction, and the S, the R, are pointing in the other direction. So again, we labeled one of the enantiomers with deuterium. We performed the polymerization under different conditions. Finally, we decided to perform this polymerization of these crystals in water. You just take these crystals, you put them in water, which contains the initiator, and then the reaction was quantitative. And what we observed, for our surprise, was very, very, very fascinating. In variance to what people expect in solid-state polymerization, where the short peptides are ordered and the long are disordered, in this particular case we found just the reverse. The short one actually were less ordered, but as you go to the longer one, and you could get up to 25 repeat units, as you go to the longer one, you could see that the wings pump out, and you don't have much in between. You get the homochiral one and one which contains 1 unit of heterochiral. And going to the multi-toph-toph, we saw that this unit is either in the two ends of the system, of the chains. And therefore, this requires now to have a different mechanism for the polymerization of these peptides in the crystalline phase. In other words, if we observe a different result than what we anticipated, we must have a different mechanism which should, in principle, account for this particular difference. And to make a long story short, what we proposed was that we might be forming, after the short peptides of 3 or 4 units are formed, they are self-assembled, but to form kind of what we call racemic beta sheets. When Linus Pauling, when he did his studies on the alpha helix and the beta sheet, he also proposed that if you're forming chains of poly R and poly S, he called them the ripple beta sheets, they should form also beta sheets. And my colleague that we are collaborating problem, Kobe Levy, is doing some force field calculations of this self-assembly of such molecules in water, and we can see that energetically speaking, these racemic ripple beta sheets are of the same stability as that of the pleated beta sheets. And since kinetically, in this case in the crystal may impose the crystallization of these chains, but I also feel that, and we shall see later on, that also in solution, kinetically speaking, the formation of the racemic beta sheet should be much more easy than the formation of the pleated enantiomorphic beta sheet. Because in crystallization, we know that if you have a system where you have RNS and R crystallizes and S crystallizes, these are thermodynamically two different systems. And therefore, on the other hand, if you take the RS, let's say RS, crystallizes in a racemic compound, this is a single crystal thermodynamic phase, and therefore the rate of formation of the R crystal should depend on the concentration of the R and on the concentration of the S, whereas here the concentration of the R and S, which will be square, and therefore the probability to forming the racemic species, be these beta sheets or be these racemic crystals, is actually much higher than the probability to get a spontaneous resolution. And we know that in crystals, many compounds, many racemats actually crystallize in the form of racemic compounds, rather than undergoing spontaneous resolution, which is a very relatively rare effect, a rare process that we have. And therefore what we said here, that we might be forming these racemic beta sheets. And I think this is very important, because according to what I mentioned before, if you want to form an alpha helix, or if you want to form the pleated beta sheet, then you have to have 8 repeat units to form this particular sheet. Whereas if you're forming the racemic beta sheet, you have to have less molecules. That's the 4 or 5 molecules which are enough to self-assemble together and to form a beta sheet, to form a kind of a beta sheet template, which might operate as a good, efficient template in the ensuing process of chain elongation. Now our problem was how to confirm that we are forming this kind of racemic beta sheet and not the pleated beta sheet. Because if you go to the X-ray, they are very similar. You don't differentiate between them. You do the infrared spectrum, they are also very similar. You get the CONH 1637, something like centimeter minus 1, you know that you have a beta sheet, but it's very difficult to differentiate between the beta sheet which are pleated and which are racemic. So what we did actually, we say, let us how we can differentiate between the two. We say that if you take an initiator which is an ester of the amino acid, because the ester of the amino acid can be a good initiator because it has the NH2, which is a good nucleophile. This ester of a given endedness, let's say if it is S, it will be attached to the R chains and it will be attached to the S chains. So if this is phenylalanine and this is phenylalanine, this chain, this initiator will integrate coherently in this particular chain. You're changing just the COH at the end with an ester group. So this will not interfere with the growth of the chains, of the mirror chains of the R. On the other hand, the S group, which is the end of the R chains, it must change its conformation. You must interchange between the groups. And if you interchange between the groups, it must interfere with the growth of the S chains. In other words, if we are looking now in the enantiomeric axis of the various chains, as function of length, well, this has now, if they are initiated with an ester, then we are anticipating that maybe in the beginning, when the reaction takes place not in the template, but takes place in between isolated molecule, the S will induce usually the formation of the S, so the short one should be reached in S, whereas once the template is formed, and the peptides which are formed in the template, then the enantiomeric axis of them should change, should be reversed.
You don't have the sandwich structure that we talked about yesterday, or was it just a lack of the plotting accuracy?
What do you mean?
Because it started with an R and ended with an R. That's just on the sketch here, right?
This
really
one. This is in solution, what I'm saying. This is now, if you take this in solution, for example, if you polymerize the R in solution, okay, in the presence of S, and then and you polymerize the S in the presence of S, if you're forming the pleated beta sheet, it should be the reverse. Because this one, the S, will inhibit the growth of the R chains, but not in S, if it is a pleated. But if you take the racemic one, should go the other way around. Is that clear? You see what I mean now? If you have this one, racemic one, the N group attached to the R should affect its near neighbor and will impede the growth of the S chains. Okay? And when it's here, if it is the pleated one, the S which is here will inhibit the growth of the R chains and not of the S chains. So there must be a complete difference in the distribution of the enantiomeric axis of the different chains which are formed if it is a racemic or it is a pleated beta sheet.
Yesterday we had the situation where if you had an R on the top with these crystals, then you would have an S at the bottom.
But this is a three-dimensional crystal.
Yeah.
Here it is a kind of a cluster,
right.
But I shall return to this point, because I think that the same concept we shall try to apply to these beta sheets as we apply it in the crystal. And we shall see that also this racemic beta sheet can induce asymmetric induction, diastereomeric induction, like in the case of the crystals. Okay, so what we did here was the following. this was in the case with the alpha-methyl ester. We saw that the tetramer, by starting with the R, which was not butyrated, actually it inhibited the growth of the R, but as we move farther and farther in the 6, the 7, the 8, there was a turnover. Okay? And therefore it was a quite clear-cut indication that we are actually observing the racemic beta sheet and not the enantiomorphous, not the depleted beta sheet. Okay, not in that now. Now the problem is, if you're forming the racemic beta sheet, if you're forming the racemic beta sheet, one asks again the same question: whether a racemic beta sheet can induce enantioselection in the polymerization process, because it's racemic, right? It has a center of inversion, and therefore. But if you look again, and this is the same principle that I raised with the glycine crystal, if you take a centrosymmetrical system, the rims of these architectures are chiral. Okay? Now these are homochiral rims, right? And if, let's say, this is the growing side, and this is, let's say, this is the left-handed, let's say the S system, this will grow in this direction, okay? And this one will grow in the opposite direction, okay? And this will grow in this direction, and this will grow in that direction. So what we have is, and this was the reason, Mark, which I claimed yesterday, that if you have artificial life for some reason, okay, then you might envisage a racemic situation where you have two different regions. You might have two different catalytic sites on each part of these racemic structures and architectures, which could induce some kind of selection in the growth of the system, or even catalysis, because as we shall see, these are pockets which are formed in the system. So this, Lawrence, what I had in mind yesterday. But of course, if you look in life, daily life that we know, of course, such systems will not be, they will be very rare and not be useful. But what I'm saying is that it is feasible in the early stages of evolution. They could have played an important role. Now, what was the compound from this point? What we learned from this experiment was the following. You need, first of all, to create certain homochiral species which can self-assemble. And if they self-assemble to form the racemic beta sheet, during the formation of this racemic beta sheet, they create the pockets and the two rims of the beta sheet. And the growth now will be controlled by these pockets which are formed. They should reduce the free energy of activation. And therefore the rate of polymerization on the template will be much faster as compared to the early stages of the system. And therefore, if you are expecting the formation of long chains, they should be homochiral. And then we say, why we should go to the crystal? Why not going directly to the solution? And as you know, in N-carboxyamide, a lot of work has been done. For Doty, Blaut, Kachalski, many others. But most of the reactions were done in this organic solvent. Because they were afraid that if you do these reactions in water, N-carboxyanhydride can undergo hydrolysis. There were a few words, I think one in Montpellier, I think people have done a very nice study on this electrochemical measurement of L, Berlin, and others, that you could really polymerize this in water. Paul Bartlett did some studies on the polymerization of this in water. But what we did, let us try to look on the distribution of the various peptides when you do this reaction in THF, like it's been done before, and to do this reaction in particular in water. And if you do this reaction in THF, you see here a very nice distribution where the heterochiral peptides are formed. And you have odd-even effect. I can explain that. But you find a heterochiral, almost binomial system. What was important here, that if you do this in water, you get a completely different distribution. You see that what you see here is that the wings are pumping out, in contrast to this. And this was with valine, but if you do this, for example, with leucine the results were even much more exciting. You can get up to, now we can get up to 30 repeat units, and as you go to the longer and longer one, you find that R20 of the homochiral, and you find N-1. As I pointed out, this heterochiral unit is in the two ends, as we could learn from the multi-top studies, and therefore you get a very nice, what we call is a very nice control by this template. Okay, now the question is how this template is formed. First of all, we studied this by X-ray diffraction. We could see very nice beta sheets. As I said, the X-ray does not differentiate between the racemic and the homochiral, the pleated sheets. And as I pointed out, if you take R and S, you get the racemic one. The racemic one has a better chance to be formed because of the reason which I just explained before. Whereas if you take the pleated sheet, each phase behaves a separate thermodynamic phase, and therefore the concentration which affects the precipitation of the pleated sheet is proportional to R, to the concentration of R or of S, whereas here it's proportional to the concentration both of R and S. And therefore the formation of the racemic beta sheet is much more feasible. Now the next point was that we did these experiments in water, by taking the N-carboxyanhydride in water, where we had the initiator, but we analyzed the supernatant, the water-soluble fraction, because the short peptides are soluble in water. And what we found here was very interesting. If you go, let's say, the dimers, trimers, and tetramers, you see here, if you go to the pentamer, you see that the pentamers, which are homochiral, and the hexamers, which are homochiral, the tetramers, which are homochiral, they are not soluble. So there is a difference in solubility between the homochiral one and the heterochiral one. So what we propose on the basis of this data that we have observed, that once the tetramer homochirals are formed, they self-assemble preferentially to form the racemic beta sheet. They also can include also N-1, but most of them since they are less soluble, they can precipitate, and if they precipitate, they form in the beta sheet. And by forming the beta sheet, now the reaction proceeds on this template, on the beta sheet. And if they proceed on the beta sheet, and the beta sheet actually exerts very strong diastereomeric control to the system, all the products which we are generating actually are of the same, are poly R and poly S. Is that clear? Mark, you have some problem.
It's not clear to me why the mechanism by which the beta sheet controls.
Okay, this is the next step.
Huh?
This is the next step.
I can't understand that.
Okay, Maui, you cannot?
I don't understand.
Oh, okay, I didn't deal with that point.
By which this.
What I wanted just to say so far is that if you polymerize so far in water, and carboxyanhydride is very in water,
beta sheet,
you are creating once the tetramers and the pentamers, which are homochiral.
I understand, but the beta sheet, the racemic beta sheet, is the covalently attached groups in the beta sheet are all homochiral.
Yeah.
The beta sheet is racemic because of the adjacent chains to it.
That's right.
And then you say that the polymerization in that beta sheet, that beta sheet influences a homochiral polymerization. Now, so the beta sheet has R chains, S chains, R chains, S chains. What's being produced?
Poly R and poly S.
Is pure poly R and pure poly S.
As the major component. Beyond
It's kind of a mixture. I mean, when you look at your data.
Yeah, but I think no. But I think that if you look on the leucine, for example, if you look on the leucine.
Now, the reason you're seeing this.
If you look on the leucine here, you see, you see that you have R13 and you have S13. 12, and then you have what you have actually. You don't have the central, the heterochiral one are very minor.
What do you have? What is that? The last one, S1, 18?
Here you have R20 and S20.
No, the last one down there.
Here?
Yeah.
here is up to 18, okay? So this is R18 and this is S18, okay? This is R17, this is S17.
Oh, I see, the deuterated one.
So this is one, and what you
The
find here
difference in
actually...
weight is the fact that you have this deuterium in the
Yeah, yeah.
But, so the transfer of information is from the water, but you're not only in water, you're on a laminar blodgett.
No, this is in water. This is pure water.
This is not the laminar blodgett.
No, these are anchor carboxyanides dissolved in water.
So
In contrast to what was
so the effect you're getting is some kind of an aggregation.
Yeah, you're getting the racemic beta sheet as a self-assembly.
The aggregation is kind of like a quasi-crystal.
It's-
It favors a beta sheet. The beta sheet is like an aggregate
Yeah,
that's forming in
Yeah.
water. So the reason you're getting a better effect, this is what, leucine?
yeah,
The reason you're getting a better effect with leucine is that the leucine is hydrophobic.
That's
so
right.
it favors
that's right,
that aggregate.
that's right.
And the aggregate likes to be cleanly.
I will tell you even more than that.
Yeah.
After a very short time, you see a precipitate.
Yeah.
And I think these are colloidal clusters. And the polymerization can proceed in a colloidal structure.
Well, there are polymerizations that occur that way.
Yeah,
But that cluster has to have a regular structure
yeah.
in order for you to continue to get.
Not exactly, we shall come back to some other examples of this not known. But I think the mechanism is that you take this anchor carboxyanide, you put it in water, it polymerizes, the tetramers and pentamers of the homochiral sequence are less soluble, they precipitate somehow, and then the reaction proceeds within this particular beta sheet temperature.
Beta sheet.
Racemic beta sheet temperature, they proceed in this racemic beta
Well,
sheet temperature.
they precipitate, and in that precipitate, the
They
polymerization
continue,
takes
continuous,
place.
yeah.
Well, you're getting the end result of this is homochiral change.
That's right. But if I start the reaction, for example, with the ester again,
Well, what's the highest degree of polymerization that you get?
I get to 30 degrees, 30 repeat units.
Very little, but some.
But now we are working on how to try to combine between different chains. Now we're doing now another experiment that after we have created these chains, we are now trying to design another method how we can combine between chains, and then after that we go to longer and longer chains.
Okay, I sort of get the general idea. You know,
Okay, so
you know,
it's clear?
Yeah, the general idea is okay.
Okay.
So what is so special about this THF? Why was that so different? Yeah,
Well, I
why
think that
did THF so different?
I think that there are 2 points. First of all, I think these are the structure of this. These are the structures of the beta sheet. Now, here we are creating some pockets, okay? And these pockets are hydrated. They're hydrated. The monomer is hydrated. So you have an interaction between a hydrated pocket
Mhm.
and a hydrated molecule. So if you take THF, maybe we know that in THF we are forming blocks. They are composed also from blocks. They are not isolated molecules, they are blocks. But I feel that they are not, you don't get this hydration of the growing site and not hydration of the N-carboxyanhydride. And therefore, the recognition of this particular pocket for the molecule in water is much better than what you find in an organic solvent.
Mhm.
But you know,
And maybe the other part is also the structure of the beta sheet, because it is a hydrophobic solvent.
Why are you getting, you know, the beta sheet is formed by the N-carboxyanhydride polymerization,
Yeah,
what they call lyxanhydride.
yeah, that's right.
Now, why should the beta sheet form RS so nicely like that?
Because I think that you are creating in a pocket.
It's not an equilibrium.
No, yeah, we have a pocket.
Yeah.
And this pocket can recognize, because it's a chiral pocket, and it can recognize actually, and if this is hydrated chiral pocket,
Yeah.
so you will come with an hydrated
But
N-carboxyanhydride.
but so specifically?
Yeah, very specifically.
That's what.
And thus in Lucid, these are really remarkably specific.
Well, I saw, but
Do these aggregates?
Yeah.
They should, these beta sheets should aggregate. I mean,
Because they are
Well, I mean,
hydrophobic. They are
just-
hydrophobic.
Yeah, they are hydrophobic, and if you look from this side to the bed sheets, let's
Yeah.
say in this direction, you will have something like fork-like structure,
Yeah,
and so this would come to complement,
that's right.
right?
That's right. Because as I pointed out with the ends, right? If I take, let's say, with this end, let's say one is going in one direction,
Yeah.
but the other chain and the other terminal group, one is the N-terminal group, which is continuing to polymerize, whereas the SC terminal group is not active.
Right.
And therefore, what happens is you can take such a racemic beta sheet, and I find this very, very interesting because biologists, after Pauling has developed this triple sheet, they ignore that completely because they don't play any role in biology. But I believe, and I want to advance this idea, like in the case of the glycine, I believe that the racemic architectures, which are delineated by homochiral rims or faces, they recognize they might have a selection between one way or another. In the case of the glycine crystal, they are actually on the surface, just you block one face and then you expose one face, and therefore you can get a nice selection that they can pick up from the food stock. They can pick up only one enantiomer. Okay? And the point was here that what we say here is that if I take now an R amino acid, again, the ester, the methyl ester, which is also a very good nucleophile, then what I'm expecting here, that if this is R, it will block, let's say, where is that one? The C is here. It will block the nearer neighbor, the growth of the nearer neighbor. And therefore the distribution, the non-numeric axis of the chains in the short one should be in excess with the same absolute configuration as the initiator. But after the tetramer, when the beta sheets are formed, there should be a reversal in the non-numeric axis.
But can only work with antiparallel.
How about?
Can only work with antiparallel.
Yeah, because if you take the parallel, and we have done that. How we have done that? We take S in solution, and we write it with S, and then it gives very nice long peptides. Where he took the R with the S, he got very short one. So in other words, this is a very nice way to separate and differentiate between the racemic one and the enantiomorphous one. So these are what we are suggesting here. You have here hydrated sites, okay? And here you have an hydrated site. Here the hydrated site is that of the one endedness, and this is of the other endedness. And if you take, for example, here another starting group here of opposite endedness, then you interchange, let's say, the isopropyl group with the hydrogen, and then this isopropyl group should block or should hinder it, and should modify the size of this particular growing site. This was again, and this is what we found here with valine. You can see very the asteromeric axis of the homochiral oligopeptide generating nucleation of RS-valine in aqueous solution in the presence of enantiomer enantiomer. In that case of S-valine, you see that the first one are in excess of the S, but after a while here in the pentamer, sexamer, you find a change in the distribution of the enantiomeric axis, which is in keeping with that. And if you do the same experiment, by polymerizing S-valine and carboxyanhydride with the S-valine ometoxy, you find such a distribution. Whereas if you do it with the R, you can see that you find a different distribution. I didn't like to plug it in the enantiomeric axis because these are two different experiments. But if you compare the size of this versus one of the normalized is one of the peaks, you see that here it goes just the reverse side. Okay? Now, the next point was the following. This was N-carboxyanhydride. Now, Luisi, and I know that Jim is not around here, but Luisi tried to use the Orgel reaction. Orgel reaction was done by taking the pure amino acid. You take the pure amino acid, which you react with carbonylimidazole, the imidazole, which is actually a replacement substitute for gene. for gin, all this can be found by Wachtenhauser actually. But that's the problem, but you don't like to work with for gin, so you work with this Stab reagent, which Stab actually found in order to substitute for gin. And if you react amino acid with for gin in water at 0 degrees for 3 minutes, then you're forming this intermediate, which converts presumably to the N-carboxyanhydride. Andre Brach at the time suggested this is N-carboxyanhydride, which can continue to form the polypeptide. Okay, so we say we want to start with pure amino acids, and we want to do these polymerization reactions in water. Okay, so what we do now, we try to say that, and as I pointed out, Luisi did similar, we did some reactions of this kind in water, and when he was doing these reactions in water, he could get up to 6 repeat units. We got an excess of the homochiral one, and Jim, I think, elaborated a model in this particular system, and he suggested that this reaction takes place by what I call a symmetric induction, Markov type mechanism. But now in our case, we found that we are forming some kind of peptide for templates, and we ask ourselves, where are the differences between the reaction of Luisi and our reaction? Now, Luisi was not using initiators. Luisi uses actually the amino acid itself as an initiator for the reaction. And if you take an amino acid at pH 6, and he was using also buffers to keep the pH around 6, 7, and then what happened was that if you take amino acid, it is at zwitterion. The NH3 does not initiate the reaction. It is only It is only the NH2, the free form of glycine, which initiates the reaction. And in this pH, the percentage of this is very low, less than 1%. And now we did some NMR studies under conditions of Luisi, and what we found that if you polymerize the system, the N-carboxyanhydride, under these conditions, you find primarily hydrolysis. The reaction of the hydrolysis is much, much faster than the reaction of the polymerization. And therefore what we say, let us try now to modify this reaction in a way that we can insert at a certain moment not the amino acid itself, but one of the esters of the amino acid. Because the ester of the amino acid is the NH2 as a nucleophile, which can really can be much better, and then the rate of the reaction of the polymerization will be much, much faster than the reaction of the hydrolysis, and therefore this might give us better conditions to get longer peptides.
By the way, just last week there was a JAX paper by Dominic Marx from Bochum.
Yeah.
And what he did similar investigations on the COS activation.
On the CO?
COS, carbon oxysulfide activation. What he found is kind of counterintuitive in a way is he's able to simulate water with these Carparnello methods under high pressure. And what is interesting is that the water, also this equilibrium between zwitterionic and neutral amino acid, is completely shifted if you go to high pressure. So epsilon is 80 something like this.
Shifted?
Towards yeah, exactly.
So what you're saying is that if you perform these reactions under high pressure, we are going to get
exactly.
This is interesting. Interesting. Okay. So we try to do this now experiments again by So we performed the same experiment now with the leucine. Okay, we reacted the amino acid leucine in water at 0 degrees for 3 minutes with the carbonyl imidazole. We raised the temperature, and now we injected the catalyst. And then what we observed Again, very similar to what we observed with the acrylic and carboxyl nitrate. We will observe exactly the same part, which was, we submitted to Jacques. We had a big fight with Jacques because they say, well, there are no kind of unclear statement made by the reviewers, so I have to try to respond to them. But what happened is that we are observing exactly the same part, which means that you can take pure BL amino acid, BL leucine, you can put it in water, you can create in the presence of carbonyl imidazole, and you can generate this particular proteins. Now the question arises now, whether it is possible.
Now wait, but what does this have to do with the beta sheet?
I think that beta sheet are also formed as intermediates. Because if you're forming sufficient amount,
If you're forming,
if you're forming sufficient amount of the peptides, of the tetramers and pentamers, they can self-assemble in the form of beta sheet, and then the rate of reaction of the beta sheet should be much faster than the hydrolysis on the one end, and with the short of the first formation of dimers and trimers, you can really generate these long peptides. But you need this peptide, you need this beta sheet in order to form that. Because otherwise, if you have a Markov mechanism, after the dimers you get, let's say, 20% enantiomer excess. You go to the term, you get 20% enantiomer, you're going to get a decay. But the moment that you're forming these beta sheets are very, very robust, I think, and especially in the case of the leucine, and then they what you call, they exert asymmetric induction, diastereomeric induction in the selection of
through
this
that
part.
hydrophobic pocket
Yeah.
that you're about.
And if you start with the
Hydrophilic pocket.
yeah, and if you start with the homochiral ester, like in your case, when you put one group here, how we call that, sergeant? You put this catalyst in the sergeant, then you can really break the symmetry. You get excess of one independent with the other. Now the second question now arises, what is the nature of these pockets? Are these pockets capable to separate, to recognize other amino acids of the same adenine, okay, and to get copeptides? If I mix, let's say, 2 racemic mixtures or 3 racemic mixtures of amino acids, should I be able to get homochiral copeptides of one adenine versus copeptides, let's say, and not to be what we call something which is random? And the first experiment that we did was the following. We took, first of all, D-isoleucine and L-leucine, okay, with the L-methoxyester. And what we did 2 types of experiments. We took L with L, L-leucine and L-isoleucine, and we took L with D, D-leucine with L-leucine, L with L and L with D. And what we observed was the following. When you take L with L, you get a random distribution of the L in the L channel. You get a copeptide, which the product, this is with a random sequence. The L-leucine dissolves in the L forms, we forming chains composed between L-leucine and L-isoleucine, okay? Whereas if you take this L with D in water under the same conditions, you get beautiful polyleucine and polyisoleucine. And this was a nice indication that these pockets of the leucine at the racemic beta sheet can recognize between leucine and isoleucine of the same adenines, but they don't recognize between leucine or isoleucine of opposite adenines. So this is a kind of a copeptide which is formed under this condition. Now, we wanted to introduce some hydrophilic.
But you mean you're getting the D and L in single chains?
Yeah. No, L and L in single chains, but D and D. If I take DL, leucine, and D isoleucine, I get polyleucine and polyisoleucine.
Oh, I see.
And if you take L and L, you're getting a mixed polymer.
If you take L and L,
I take a mixed copolymer.
so the leucine and isoleucine are in single chains.
Yeah.
I see. So in other words, it's more sensitive to the chiral difference than to the structural.
Exactly. You put it very nice. Okay. Now, we wanted to take some hydrophilic amino acids because, if we want to make finally, as I pointed out, one of our challenges is to try to design some peptides which might have finally some, let's say, some prebiotic catalytic properties. You have to incorporate some hydrophilic amino acids within these chains. Okay? So we try to do this with.
Well, it's a random, but the leucine and isoleucine, even though they're all L, they're in there in a random way. I mean, the system.
There are blocks.
The system is not selecting.
No.
There's no primary.
But if you take poly L and poly D,
yeah, well,
system.
no, they're different. You know, you've got different chains. But the interesting thing would be if the system had some primary structure selectivity. You know, if you had a bunch of L amino acids.
What do you mean? A mixture of elements.
Yeah, if you had an extra different.
Wait a little bit.
Well, we gotta have one. Well,
Okay, another few
How long
minutes.
do you have to go?
Another 5 minutes, no more. Because this is the punch.
Gotta get something to eat.
No, I want to do the punch. But you're asking questions, you want answers to your question, right?
Oh, punchline. Well, I understand.
But then?
No, I said, I'm just trying to understand.
Okay, I understand, that's right. But you want to eat something, right? What is more important, to understand or to eat? Okay.
It's surprising what you're finding here.
Okay, so what we did actually, we tried to do something else now. We wanted to take histidine. But Peter, Peter Stravinsky, actually reported in Barcelona that when he tried to polymerize by the same method histidine, he was getting the urea. It was not possible to get the carboxyl. But we took N-methyl histidine, which is also hydrophilic, and it does not form. It does not form
What do you
the
mean
beta sheet.
N-methyl? Where's the methyl?
We can get it in both sides, non-methyl way.
It's on the histidine ring.
I understand the ring.
On the two sides.
Yeah, because if you take there, you have a reaction there which is forming the urea rather than forming the carboxyl, you don't get the product. And then you don't get the polymer of L-histidine and methyl. You don't get the long polymers of N-methyl. Because if you do it with phenylalanine, you're getting only the polymer of the phenylalanine. But if you take L with L, you get, the copeptide here. Okay? And what does it mean? That if you take L-phenylalanine with L-methyl, you can get the copeptide of the phenylalanine. And so this is not what this indicates. But if you take D with L, you're getting only that one of the phenylalanine. So in other words, this can be incorporated in the chains of the L, but it's not incorporated in the chains of the D. Phenylalanine.
Say that again.
If I take, let's say, D-phenylalanine, D-phenylalanine,
and L
with
methyl.
L and methyl histidine, I'm getting only polyphenylalanine. D.
Why doesn't histidine form its own chain?
Because it is hydrophilic.
It's what?
It is hydrophilic.
I see. So it doesn't form.
It doesn't form the beta
pockets
sheet.
and,
It doesn't form the beta sheet.
Beta sheet doesn't aggregate.
Also nucleophilic catalyst.
Yeah. Yeah, it can be, but I don't think that it participates because it is N-methyl histidine.
But it still
No,
can
but
form.
still, if your N-methyl histidine is a perfect nucleophilic catalyst. And the attachment of the side chain is not at the nitrogen of histidine. It is at the 4 or 5 position. So it can be a perfect nucleophilic catalyst.
It can be it can participate in the catalysis with that. That's possible.
Yeah.
And also, we thought that maybe imidazole can do it as well, but we never found imidazole at the end when we must detect it. In other words, if this is correct, we can detect it by mass spectrometry, but we don't detect it. Because in case of imidazole, we think maybe it will go after the hydrolysis. So we don't
It's
find
a nice trick to use this N-methyl.
What?
It's a nice trick to use this.
Because this, if you build up the model, I don't like to enter into that. We have an SN1 reaction, which is forming the N-carboxyamide, and if you do that, you get a different conformation, which cannot compete with the formation of the N-carboxyamide. So let's come to the last part now. I think the last experiment. So what we want to do is now to take different racemic amino acids. Okay, we took a number of different racemic amino acids, and I'm going to present here one of them where we can see by mass
The
spectrum.
hydrophobic ones gave you the homochiral chain and the hydrophilic
Yeah,
ones didn't.
and they can be they can be templates. Within, you can incorporate some other amino acids. In this case, we introduced tyrosine and N-methyl, imidazole, alanine, and leucine, of course, another phenylalanine. So, but the analysis of this mass spectra are very complicated. I don't like to bother you with that. But I would like just to
Why
show
don't you
one.
take the hydrophilic amino acids and put them in a hydrophobic solvent, and that's been modified to some extent so you can get enough.
This is a nice example.
Get the active. In other words, do the opposite.
I think that this is feasible, but as I say, I will driven by the question to do the reactions in water. But what you're saying is a nice experiment. I agree with that. I think it's a nice experiment because
You have to play. You got to play with the solvent. In that
I
system.
just got a letter from Andre Brack. He showed me some polyasparagine, forming very nice, what they call serpentine, like
Spock
peptides.
from Spock and Block. You mean the guy who did the DL many years ago?
Not the no. He did it. Yeah, this is the same guy.
Block and Spock.
Brack.
French. The French.
Yeah.
They're
Brack.
still around. Those guys?
Yeah. He's retired, but he's quite active. He did these studies with the circularly polarized light, or the decomposition
Also,
of the
he made
lucid.
He made DL peptides years ago.
Yeah, but this is different. We are in contact. We are in contact
But
with
that's
him
how
and
I
the
know
public.
of his work.
Yeah. So what we did here now, and let me just see the problem, because DL phenylalanine, DL tyrosine, DL alanine, these are three groups that we have used. And I just want to show you because I can really separate here between the various copeptides which we have. So if you take phenylalanine, you see just the homochiral, okay? You take phenylalanine with 1 unit of alanine, you get it here. You get phenylalanine with tyrosine, 1 unit, you get only the homochiral one. You get here phenylalanine 5, and then now you have phenylalanine, tyrosine, alanine, you get this formula. You take phenylalanine, alanine 5, 1, tyrosine 1, 6, and we get up to 8 units. So these are, because we have more material, of course, with distribution, we get shorter peptides. But now what we're trying now to do is to initiate this reaction with the thioesters, and the other then the thioesters, and then now we're trying to combine between the various chains. And then if we can combine between the various chains, maybe we can double and triple the molecular weight of these copeptides, and to get some homochiral copeptides starting from particular mixtures of racemic amino acid.
Now, if you take an already formed data sheet and you pegylate it, put something, so you can get it into water.
It's a problem. We try that because always in our reviews, always they say, well, why you don't synthesize the racemic beta sheet? Because if I synthesize the racemic beta sheet, put it in water, you lose the information.
I'm not one of the reviewers.
I don't know. I suspected you.
No, I'm not one of the reviewers. I just asked that question independently.
Okay, that's right. The problem is the following, that there's something interesting. This is what we're trying to find. As I pointed out, we are forming colloidal particles. And these colloidal particles, the pockets within these colloidal particles are responsible for this selection. Now, if you take these peptides and you remove the water and you try to put them again in water, you cannot continue the propagation of them, because we say let us try to increase the molecular weight of these chains by taking these peptides, putting them again in water and trying to polymerize. It doesn't work. What does work is that as they form, probably they are strongly hydrated.
Well, that's why I wanted
And
you
therefore,
to.
if they are strongly hydrated,
That's why I wanted you to put a polyethylene glycol chain on it.
yeah.
To peg, what they call pegylate them or something. That's a word they use. Because then you would give them a chance to come to some kind of equilibrium state in the water. That would be like soaps in a way.
Yeah, it's possible, because I think that
The peg chain
of
would make it like a
sheets are
soap.
very important.
You don't want to just put the beta sheet in. You want to put it in where it's the hydrophobic part of the soap.
Yeah, this is possible, because I think the state of that is very important for the chemical reaction. So again, I think that I will stop here and just want to mention my coworkers, Dr. Isabella Whitebrook, with whom I'm working now for several years with me, and this Ronnie Royce, who did these studies, and the guy from Argentine that spent some time.
By the way, I thought of Lipson's man. His name was Clifford.
Clifford.
But I don't remember his last name.
Clifford, I know. Bauer.
Clifford.
Okay, so thank you for
Thank you very much.